Right. So with truth and beauty on our minds, I will talk about 20% fine-tuning and supersymmetry. No, so in all seriousness, I do want to just recap the sort of tuning numerology that we were. Oh, this is no, it's on. Okay. That we were doing yesterday morning. And I'm going to write down numbers corresponding to roughly 20%-ish fine-tuning if the scale of supersymmetry breaking is low, right? So if you say 20% fine-tuning with this measure I gave you earlier, the delta mh squared over mh squared over mh squared over 2, as your definition of what 20% means, you find that the mass of the stops, sort of average mass of the stops, also the mass of the left-handed sputum, because you can't separate that much from the mass of the stops. That should be less than about 600 GeV. The mass of the gluino, less than about 900 GeV. Mass of the hexeno, less than about 200 GeV. And then everybody else is pretty weakly constrained. We know above 900 GeV is, I guess, the next, below about 900 GeV is the next one that kicks in. And none of these are magic numbers, right? The fine-tuning measure is a little bit arbitrary by a factor of a couple. 20% is just one of many lines you can draw in the sand. Basically, the tuning scales quadratically with the mass above these limits. So, you know, answering the question, is nature 10% tuned or 20% tuned, is completely uninteresting. Okay, but I think answering the question, is nature 50-ish% tuned, or is it more than 1% tuned? That's something that's worth knowing. Okay, and the kinds of gluino mass limits that we're talking about for asymptotic LHC, if nothing is found, at least in sort of canonical, our parity-conserving jets plus met SUSY, which you can see with jets plus met searches, we're talking about sensitivity up to around 3 TeV for gluino masses. So that's taking you another factor of 10 beyond this in tuning, at least. That's taking you to the couple of percent level, and with high energy LHC, conceivably higher. So we are on the march now. This is what I was trying to stress earlier. Every step of the way isn't that exciting, one step at a time, but we are on the march from really not knowing in any bottom-up sense whether SUSY could consistently be solving basically all of the hierarchy problem, to knowing that at least in SUSY, there's some inherent, unavoidable bit of fine-tuning. Okay, and this is going to be SUSY specific. We have the same discussions in the context of compositeness as Raman's been talking about. We should have the same discussions in the context of every theory that we collectively can contrive to explain the hierarchy. But, you know, I don't want to get too distracted by the 20 versus 10 questions. The reason I'm putting this up here is as a benchmark, because this is a scale of sensitivity that's been reached for already, just in the last year-ish, for jets plus met searches. And now we have to ask, does that really mean that we know there's no SUSY below that scale? How does the sensitivity compare in other final states? And I think that the only way to do it is to sort of ask, how are we meeting this benchmark? Or where are we going? So compare this baseline scenario of just universal squark and gluino masses to other possibilities for the spectrum. Where is there room for conceptual improvements in the way searches are done? Where are we just marching ahead at the right speed, in the right direction as best we can? So I'll start by reviewing the sort of sensitivity of jets plus met searches, and then I'll gradually expand the field of interest to cover some other possibilities. First, just what happens when you get rid of the light squarks, decouple them, and then talk a little bit about taking away some of the missing energy of the standard MSSM picture through various decays of the LSP, sort of motivational issues concerning that, and then different kinds of searches. So let's see. So the very simplest case you might think of, if you have that kind of hierarchy in mind and squark mass universality, would be if you have a heavy gluino, all the squarks somewhere below it in mass, and then maybe a Higgsino and a Bino, maybe a Wino, some neutralinos down here, others might be decoupled. This is one kind of scenario we might think about. Could also reverse these and ask what are the constraints on this kind of physics. Now, as I stressed yesterday, it's very simple to figure out. Here it's almost too trivial to figure out what basic scenario is going to happen, how this will be manifest at the LHC. The gluinos and squarks will be pair-produced considerably, particularly the light generation squarks. Right? Light generation squarks are much more efficiently produced than bottom and top squarks because there are diagrams, T-channel diagrams. That let you use valence quark PDFs to produce them. And large C quark PDFs, which are absent in the case of top. And in addition, so you mostly produce the first two generation squarks and the gluinos. The squarks here would just decay to, and this is some complicated, potentially neutralino sector. The squarks go to either a neutralino or a chargino plus a jet, and the gluino most of the time goes to a squark plus a quark through the Gaugino-Yukawa interaction. So when you produce two gluinos, this gives you very roughly 4 jets plus met from gluino-gluino. From gluino-squark, 3 jets plus met, and from squark-squark, 2 jets plus met. This is assuming they decay either right down to the bottom here of the spectrum, or they decay to some higher neutralino or chargino, but the splittings are small enough that you can basically ignore anything produced in the cascade. Yeah? I'm imagining the Higgsino down here, near the bottom, and I'm not worrying too much at this stage. We'll discuss cascade decays in 1 second. But for now, I'm imagining that the Higgsinos and, say, the Bino are both pretty light. So near the bottom of the spectrum. So in this case, I can show you the results from the 20 inverse, well, I'm not going to show you results. I'm going to draw a cartoon of results from the Atlas jets plus met search with 20 inverse femtobarns. Maybe I'll try to keep it on the same board. If you draw an M squark versus M gluino mass plane, and you imagine sort of 1400 on each side, there's sort of an exclusion that looks, well, exclusion that sort of asymptotes. If only the squarks or only the gluinos were light, you'd have exclusion sensitivity up to about 1400 GeV. If they're both sort of simultaneously light, you can get up to 2 TeV mass sensitivity already. This is the sensitivity if the LSP is near massless. It doesn't change very much until the LSP mass gets to about 700 GeV. And at 700 GeV, it really falls off a cliff and starts looking more like this. Okay, so you're really relying on the huge associated production cross-section. This is for MLSP equals 700. This is for MLSP equals 0, and then higher than that, it would just shrink back down. Now, of course, this 700 already takes a fair bit of tuning because it's telling you that the Higgsino is 3 times heavier than our benchmark. But and getting to this 1400 is also in itself a bit of tuning. So clearly, the kind of benchmark scenarios we were interested in for these sort of very canonical-looking models where all the squarks are at universal masses, even the 20% tuning benchmarks are pretty ruled out. You have to go towards the 5-ish% tuning to find models that are still allowed in this equivalence class. Now, it's really a little bit surprising when you first look at it, why this sensitivity drops off so sharply as the neutralino mass goes up, right? But what's happening, the way I like to think about it, I guess when Nima lectured, I think he talked about how the production cross-sections scale with mass, right? It's basically because of integrating the PDFs over threshold. Is that a yes? Yeah. So you have cross-sections that scale like square root of s hat min, which is usually twice the mass, to the minus 5 or minus 6 type power. Now, usually for total production cross-sections, this is just the mass. Once you start talking about a search like this that has rather stringent cuts, for low masses, in fact, for most of the masses they're sensitive to, the threshold isn't really set by the mass. This S hat threshold is really set by the cuts. And so the cross-section times acceptance, if you look at sigma times cut acceptance, for fixed LSP mass, varying gluino mass, it doesn't change very much with gluino mass. Okay? It's approximately independent of gluino mass. This isn't quite true. There's near threshold effects and there's non-relativistic effects in the ratio of gluino and LSP masses. But very roughly, it doesn't scale like the 5th, 6th power. It's sort of slowly varying because morally there's some S hat min that's just coming from the cuts, from how much kinetic energy the jets and the invisible particles in your final state need to have in order to pass the selections of that search. So that's slowly varying with the gluino mass. And then as you change the LSP mass, the distribution of energy changes. And at roughly the same LSP mass, independent of gluino mass, this acceptance falls down such that that product goes less than whatever the sensitivity is of the search. Right? So if the search is sensitive to 100 events after such and such selections, based on the systematic uncertainties and the statistical uncertainties, then there's some threshold at which you cut through it, which is fairly insensitive to the gluino mass. In other words, which tends to, what I'm saying is it tends to look sort of boxy, right? To some approximation, there's a gluino mass versus LSP mass contour that looks boxy. And the way of thinking about it is as you go up, you're reducing the acceptance. As you go out, you're reducing the cross-section. You can sort of fall off a cliff where this becomes lower in both directions. Just to give some vague understanding of why the acceptance contour, why the exclusion contours typically look so boxy, and why it's essentially, the searches are essentially obliterated above some LSP mass. And this, by the way, just like this limit is moving outward with more data, so is this upper limit. Because it's not like some catastrophic cliff you're falling off of, it's just a sigma times acceptance getting below your threshold by factors of 2. All right, so this is somewhat sensitive to the rest of the model. I showed that this is sensitive to, say, in the limit that you just have a gluino mass limits go up to about 1400 GeV. As you start adding observable cascade decays, the sensitivity of the jets plus METS searches gets less efficient. But most of the cascade decays, anytime you have cascade decays in the MSSM, it's basically coming from a small number of interactions. It's basically coming from the Gaugino-Higgsino and Gauge-Higgs boson interactions, right? So you have, for example, the Wino-Wino Z interaction. You have the analogs of this with the Zeno and or neutral Wino and the W. You have the often more important. You have the Higgsino, ZW, and you have Higgsino, you have things like Wino, Higgs, and of course this will also produce Z longitudinal, W longitudinal. And so most of the time, when we're talking about cascade decays in the MSSM, you get some combination of Higgs's, Z's, and W's. You can also get from certain kinds of, from Chargino cascades, here you can get gammas. But in terms of neutralino cascades, we're mainly talking about ZW Higgs, and it's hard to get to arrange situations where there's essentially no Z's and W's. That means you're going to get leptons a good fraction of the time. And from the simplest cascades, one lepton searches are sensitive up to about 1200 GeV and 600 GeV LSPs. So a little weaker, but still marching in the right direction. Now, all of these searches are going to improve with time. It's not an automatic improvement. The systematic errors, I mean, a lot of work needs to be done on the experimental side and on the standard model background side to make sure that as the statistical errors improve and as the reach out to higher energy goes on, higher energy cuts, that the systematic errors are also kept in check. But that is a sort of, I mean, this program of searches is marching on towards giving us decisive answers about fine-tuning in this kind of spectrum. Now you can go ask about even longer cascades, and then this sort of situation continues. The sensitivity of these one lepton searches starts deteriorating just because there's kinematics where the jets aren't hard enough, the leptons aren't hard enough, the missing energy isn't hard enough. But at the same time, multi-lepton searches are picking up. And you need a lot of cascade complexity to hide a 1-TeV gluino. As an example, even if you were just looking at one lepton searches with a pretty dramatic two-step cascade, say gluino goes to neutralino, here, or chargino, which goes to another neutralino, producing a W. And this guy goes to the LSP, producing a Z. So you have a WZ in each final state, and significantly degraded missing energy in jets. Even so, because there are quite a few jets, this one lepton search is still sensitive to gluinos up to around a TeV. In order to degrade that sensitivity with cascade decays, what you really need is models that stop producing so many leptons in the cascades. So I told you there's always going to be W's and Z's, and they're always going to decay to leptons. In the MSSM, there are models, and I'll come back to them later, where you aren't talking about cascading from one MSSM particle to a lighter MSSM particle through basically standard model gauge and Higgs interactions. Instead, you're talking about the, well, these are all basically the supersymmetric relatives of standard model gauge interactions. Instead, you might be talking about decaying to a new singlino that's lighter. And that decay might happen through a beyond the standard model singlet that mixes with the Higgs. And then you don't expect to get leptons out. You just expect to get BB bar. But that is hardly so that's another possibility. The other thing I should mention, just in the context of MSSM, I mentioned even the sensitivity isn't that degraded when you're forced to go through 2 cascades. But in reality, in these kinds of models, you usually don't get forced to go through that many steps of cascades 100% of the time. For example, here, if you have a Weno and a Bino, the left-handed squarks will decay preferentially to the Weno, the right-handed will decay to the Bino, and the more Bino-like LSP, and whichever one is lighter, that's going to give you a harder jet signal with more missing energy. So you don't completely shut them off in the MSSM. All right. So let's move on to and consider, well, what if we don't have that exact spectrum, right? There are a lot of assumptions built into that. One case that's received a lot of attention recently, but is actually a very old idea, is so-called more minimal supersymmetry, now through somewhat Orwellian coincidence, now known as natural SUSY. I really... Nobody's to blame for this naming choice, but it's horribly misleading. If we had seen completely unified, strongly interacting quarks at 300 GeV at the tevatron, and somebody said, no, the natural SUSY spectrum is having just a light stop, a gluino, somewhat heavier, and then all of the other squarks decoupled, and a light Higgsino. That's the natural SUSY spectrum. What's going on at the tevatron? You just would have been laughed out. This is the minimum that's required by naturalness. Push everything else out of the way. But going back, the original motivation for thinking about this was actually a good one, which was the flavor constraints on light generation squarks. Right? So the idea was, if you have some non-mass degenerate squark sector, remember the squark mass term say for the left-handed squarks. If I reinstate the flavor indices, this is an SU3Q. So this is an anti-fundamental. This is a fundamental index of SU3Q. This is a flavor octet and singlet piece. If the singlet piece dominates, there's no flavor issues. But if there's a new flavor octet contribution, then that's order 1, then the constraint on these squark masses is actually quite severe. It's actually in the hundreds of TeV range. And so the motivation was, well, we can relax this considerably by letting these squark masses drift all the way up to the point where they would start contributing to quadratic divergences. Right? So consider just this minimal spectrum, which is all you really need to ensure naturalness. It is the most minimal natural SUSY. It is not the most natural SUSY. Okay. But it's an important thing to consider, because a legitimate criticism of the bounds we talked about over here is that with the exception of the gluino bound, you're setting limits on particles that actually have nothing to do, very little to do with the hierarchy problem. And in fact, even the gluino bound over there isn't that directly applicable to gluinos that decay the way a gluino does over here. Because here, the gluino would mainly go to top stop, the stop to either top hexeno or bottom charged hexeno, and then maybe that charged hexeno would go to relatively soft stuff. In some cases, it might be visible, plus a neutral hexeno. You're not exploiting the possibility that in this hierarchy, which is an interesting and motivated one in its own right, just not by the fact that it's more natural, it has other motivations, like the flavor one I mentioned. It also is a hierarchy that arises pretty generically in models where you say it sort of combine the idea of compositeness of the sum of the fermions with supersymmetry to protect the Higgs, and say the stop is composite, then it naturally gets a smaller supersymmetry breaking mass than elementary first two generation quarks. So those are some of the motivations for thinking about this. But the gluino decays very differently. And the search we considered over there, jets plus missing energy, isn't entirely the best one to use to look for it. You often have leptons from the hadronic decays at the top. You have a lot of B jets, and the distribution of energy and of jets is different. Right? Here each top can, in principle, if it decays hadronically, produce 3 jets. But they all tend to be a little softer than the ones you'd get from direct decays over there. Now, at this point, there's been a lot of dedicated search effort, looking both for these gluino decays and for direct stop production. And the bounds on the gluino are pretty comparable to the ones we considered over there. And the bounds, this is for MLSP, less than about 600 JeV. And the bound on the stop, direct bound on production of the stop, requiring a somewhat heavier, somewhat lighter constraint on the LSP, obviously, are in the range of 600 to 700 GeV. Now, I should put an asterisk on that bound, because there are some interesting, I'm not going to talk about them today, but there are some interesting subtle regions of the stop parameter space where these bounds actually don't apply because the tops are typically produced with very little momentum. So there's some interesting regions of decreased sensitivity for the stop searches at low masses. I have to say that I don't lose sleep at night about them, just because where there's a stop, there should be a gluino. And if we don't see the stop, we'll still see the gluino and the stop in the gluino decay. But in terms of having a sort of complete constraint on these models, that's an interesting region to think about improving. Now here, I think there are some experimental challenges that might prove a little harder to deal with at high mass. Among them, any searches relying on B-tagging get much harder above a couple of hundred GeV, because B-tagging efficiencies really start petering out at a few hundred JeV. It just becomes a lot harder to resolve the B vertices in the silicon detectors. And you can use lepton tagging from the decays of the Bs and so forth, but that's less efficient. Also, in some of these cases, the top quark could actually end up boosted. And so you have to start using the sort of top jet reconstruction techniques to be sensitive to that. I think there may be some more room for good ideas from theorists, from phenomenologists, about how to search for these. But again, by and large, I'd say the search is marching on. So far, we've looked mainly at sort of jet plus maybe some Bs, maybe some leptons plus missing energy topologies. And these are motivated by this classic cascade picture that if you start from, say, a gluino pair production, it's going to decay first through any kind of strong interaction that it has, say G3 or top Yukawas to a top and a stop. And then if the stop's the lightest colored particle, it's going to decay through standard model weak interactions. Maybe it'll go to a top plus a neutralino 2. And then that neutralino 2 only has weak interactions, and it will decay into, say, a W plus chargino 1, and then so forth. Okay. Now this part of the story is dominated by large couplings, right? If we ask what's the width for a gluino to go to top stop, it's pretty large. And so if we ask what's the branching ratio, if I add some new physics to the standard model that's relatively weakly coupled, so I wouldn't have already been blown out of the water by it, then I end up with a branching ratio, it's gamma nu over gluino to top stop. Sort of kinematic scales are roughly the same. The coupling here is order 1. The coupling here is small by assumption. And this new physics isn't going to change the gluino decay very much, nor the stop decay, nor these neutralino decays, until you get to the LSP. If you think about it, LSP protected by R parity is actually one of the most sensitive probes we have of very weakly coupled physics, because the standard model width is 0. So that means that the total width is going to be dominated by any new physics that exists that could allow it to decay. So you can have 100% branching fraction, even coming from interactions that we normally think of as quite weak. So for example, we could have some new standard model singlet S and singlino, so a scalar singlet singlino, or a scalar or a gauge boson, and it's eno. And you could have neutralino 1 going to singlet plus singlino. This sort of thing arises in hidden valley models. It arises in the NMSSM, where you're adding a singlet that's just pure standard model singlet, no new interactions. Many possibilities. Even more prosaically than that, you could have your neutralino decay to some gauge boson plus a gravitino. We know there's gravity, and if it's going to be rendered consistent with supersymmetry, there should be a gravitino. So, and then finally, there are these R parity violating operators that we talked about earlier. Now, these are three pretty broad inclusive classes of new physics that would alter the end of the cascade decay. Depending on the kinematics, this might absorb some order 1 fraction of the met, some fraction of the met, but leave some other fraction of the missing energy. Or it can almost completely remove the missing energy. So if you have something that's a decay where say, the singlino is relatively light, the singlet is pretty heavy, or if you're talking about decay to a very light gravitino plus a heavy gauge boson, where this is produced non-relativistically, the kinematics is such that you really squeeze out a fair amount of the energy for the singlino or the gravitino. Here, in the case of R parity violation, you can just not have any missing energy in the event at all. So, for example, if you look at met distributions on number of events, the usual standard model, right, it's peaked, and then there's a tail coming from top with the lepton mist, and from Z events, sort of goes out on a log scale, like some power law to high missing energy. The usual story that we look for in a jets plus METS search is some new physics that sort of goes like that. Has a big hump over it and just falls more slowly because there's a new significant source of order 1 source of missing energy in the events. The missing energy fraction per center of mass energy is higher in, say, a jets plus MET event in the Galeno model over there. If the LSP decays in one of these ways, where you have some sort of moderate squeezing out of the missing energy, you can get distributions that are very slightly a little more peaked at high missing energy than the standard model. And there's no reason particularly to expect the rate for given S hat to be larger than those Z and top production rates. Those have significant cross sections too. Again, it's just the same S hat going into both. In the case of these R parity violating decays, you can actually just fall with the standard model missing energy. And there's a little bit of disagreement in the literature about the state of these. When you look at these, so some papers have claimed that actually, if you just look at R parity violating models and the W's produced in cascade decays, the missing energy from those W's, that there are enough events at high missing energy that you can actually set relevant constraints from the jets plus METS searches. On the other hand, when you look at these missing energy distributions after the other selections, they just pile right with the standard model. So I think it's not enough to count events in that kind of situation. You really need to look at how that would actually go through the analysis, whether you could actually see that over, or whether it would just be reabsorbed into uncertainties in the background. Obviously, if this was an order 5 correction to the normalization, they wouldn't absorb it in the uncertainty in the background. But if it's a 30% change to the normalization of the standard model yield, you have to be really careful about that sort of thing. So I think at worst this is invisible to the missing energy searches, and at best you can set some exclusions, but they're highly systematics limited, and the prospect of discovering it convincingly in jets plus MET is nil. It's somewhere between those two possibilities. So I'll talk a little bit about the motivation for thinking about these. I think the best case for thinking about them, frankly, is just the fact that we're not seeing supersymmetry anywhere else. So if there's nothing truly hideous and abhorrent about these models, then we shouldn't close our eyes to them. In the case of this sort of gauge mediation motivated example, X plus gravitino, and this is pretty simple to understand. Of all the super partners that we could imagine adding beyond the MSSM ones I talked about yesterday, the only one that we really should add is the gravitino. Its mass is set by the sort of fundamental scale of supersymmetry breaking. So some F-term VEV of some field, or of all fields that contribute to supersymmetry breaking, divided by the Planck scale. Compared to our soft masses, which typically go like couplings, times some F, some relevant F, whatever F is directly mediating to us, over some mass scale. And if we're talking about low-scale mediation of supersymmetry breaking, to explain why the spectrum might not have suffered from many, many decades of running, then it's natural to think of this F and M as being relatively low scales, too. This F, strictly speaking, can be different from this F, so we don't robustly know the mass of the gravitino. But if this Fs and F0 were, say, in the 100 TeV range, that would give a gravitino mass in the EV range. So this is certainly light enough to be produced. And once it's kinematically accessible, there's a very simple scaling estimate for the width. It's pretty universal. If you have an LSP or anything else that can decay two-body to the gravitino, just goes like m chi to the fifth over this f naught squared. If you had a three-body decay, say because of phase space, which is not very plausible given most of the current limits, then there would be extra three-body suppression. But just in this two-body case, say for 100 GeV LSP, 100 TeV F naught, that would correspond to about a 0.1 millimeter lifetime. So for Fs of reasonable interest, just varying this F over a few orders of magnitude and varying m chi by factors of a few, we can easily range over models that have prompt, displaced, or say outside the detector decays. Okay? If it's outside the detector, it reduces to the previous case. We don't need to talk about that anymore. We see absolutely no effect of that light gravitino if F's high enough that this decay length is larger than the tens of meters that you'd be sensitive to. If it's displaced inside the detector, there are several kinds of searches that are sensitive to that. If it's prompt, then we really care what it's decaying into. The most familiar case, in most studies, is a Beano LSP. Decays to a photon most of the time, as z is a small fraction of the time. It's set by sine theta weak. And of course, the diphoton searches are pretty good, as are single photon. So anytime you get photons appreciably, which is the case for both Beano and neutral Wino dominated LSPs, you get enough photons that prompt photon signal is pretty good. But if you're in this more minimal regime, where you have really a nearly pure Higgsino LSP because the Beano and Wino are decoupled, then there's sort of comparable order 1 branching fractions to Z plus gravitino, or Higgs plus gravitino. The Z has a high background and a low leptonic branch fraction. The Higgs can be seen in BB bar. Sometimes produces W's. So there are ways for sure to look for these decays. But this is certainly harder to see than a whopping missing energy signal. And it's not at all crazy for that Higgs or Z to carry away a good fraction of the missing energy. So this is one reason to think hard about signals with significantly lower missing energy. Another reason, another case that I think we really have to look at seriously before saying how much we know about tuning is our parity violation. So our parity is just a global symmetry under which standard model particles have, and the second Higgs have charge 0, they're even, and all their superpartners are odd. Okay, so superpartners are odd. that lets you forbid interactions like, and that means you can think about that as saying that the superfields Q U, D, L, and E, see that these are odd, that the Higgs up and Higgs down are even, and that theta is odd. So then the lowest components of these are odd, the lowest components of these are even, and the fermion component reversed. So that means that you can't write down. This would forbid the terms that I asked you to ignore yesterday, talking about the Lagrangian. It forbids terms like this one, which will be the main one I discussed today. Okay, where I'm suppressing flavor indices. Why might it be a good idea to suppress these? Well, one motivation is that it gives you a freebie dark matter candidate in the form of the LSP. It also saves the proton. Right? So if you have all of these interactions, this violates baryon number, and these two violate lepton number. And these allow, for example, have a proton go to a strange squark bar, and then this go to a neutrino and a d-bar quark. Combine that together. And you have a proton decay operator suppressed only by the mass of the strange squark and by these couplings. And that requires the product of these two couplings for TeV scale masses to be something like 10 to the minus, well, 10 to the minus 30, 20 something. Enough to compensate for, for the mass ratio of TeV to the gut scale. So this is a really huge constraint. And by the way, the couplings you need to get a decay inside the detector are in this sort of 10 to the minus 4 to 10 to the minus 6-ish ballpark. In order for, the couplings you need to get an Eno decay inside the detector are in the neighborhood of 10 to the minus 4 to 10 to the minus 6, depending on exactly what kind of LSP you're talking about. That would lead to ridiculously fast proton decay. Okay, so imposing our parity gives you a dark matter candidate. It saves you from this precipitous proton decay problem, clearly at odds with the world we live in. It also saves you from dinucleon decay, other more weakly constrained but still constrained operators, neutron anti-neutron oscillation, and some flavor constraints. So that's why you might want to conserve our parity. Now, dark matter, Neil Weiner will tell you lots of ways to get dark matter next week. There's very good evidence for dark matter. It would be beautiful if SUSY solved dark matter problem and the hierarchy problem at the same time. But there are a lot more models for dark matter out there than there are solutions to the hierarchy problem. Dark matter is very cheap. Very important to find, but from a model perspective, very easy to obtain. Right? So we shouldn't be afraid of losing one dark matter candidate. We could just go to the dollar store and buy 5 more candidates. The proton and these flavor constraints are actually relatively easy to save as well. So I do want to save the proton. Buying protons is hard. But one way to do that, so how can I save the proton? I could say baryon number is violated, but lepton number is conserved. For some high energy reason, the lambda and lambda prime couplings are essentially negligible. Only the lambda double prime is non-zero, or vice versa. And then you just need to make sure that especially the light generation versions of that other coupling are sufficiently small. So each of these has IJK flavor indices. Whenever you have any of them equal to 1 or 2, there's generally constraints in the neighborhood of 10 to the minus 3 to 10 to the minus 6. That's one approach. Maybe they're all just a little small. This is generated at loop level or something. Maybe there's some flavor structure that ensures that actually the light flavors have much smaller. The light flavor R-parity violating operators are much smaller than the heavy flavor. That's one consistent scenario. Another option is that actually if you just take, the generic operator here has a weird flavor structure. But there exist R-parity violation textures consistent with all the flavor structure coming from the Yukawas. So I could write an interaction, for example, of this form where lambda double prime IJK goes like an up-type Yukawa, a down-type Yukawa, another down-type Yukawa. Now these A, B, and C are all quark flavor indices, and they can all be contracted together into an epsilon ABC. And this is the only SU3 to the 5th flavor breaking in this texture is coming from the quark Yukawas that came in here. So in models that realize this texture, this can be multiplied by an order 1 coefficient. And because because there's no up and down type Yukawas in the lepton sector, the analogous operators are suppressed by neutrino mass operators. You end up with these lepton number violating interactions being much, much smaller. So and these are naturally, even with order 1 coefficients, small enough to suppress the flavor problems. And the products are small enough to suppress proton decay below observable levels, even for order 1 coefficients if you have this flavor structure. So this is the idea of minimal flavor violating, R-parity violation, minimal flavor violating SUSY by Chabachaki, Yuval Grossman, and Ben Heidenreich a few years ago. So both of these possibilities, I think, serve to resolve the real problems, the real inconsistencies with R-parity violation. And so it raises the question, if this is the way nature works, will we see it at the LHC? Are we sensitive to it? Is this always going to be a lurking possibility of how the hierarchy is solved? However contrary to some of our prejudices these specific models might be, is it always going to be a possibility lurking there, or can we test it? So I'll just talk collectively about testing all of these scenarios, whether R-parity violating, or some new sector, or these kinds of MET-suppressing decays to gravitinos, how do you search for low missing energy? SUSY. I'm guessing this is an area that actually won't get that much of discussion in the experimental time. So I'm just going to try to skim over it and give some references in the remaining half hour. So very broadly, there are two strategies. Okay. There's the strategy of be lucky and work hard. Or you can work very, very hard. To make sure that even in the unluckiest versions of these scenarios, you still have some sensitivity. How can you be lucky? Well, I mentioned that the range of couplings that leads to invisible decays isn't sort of precipitously, to displaced decays, isn't precipitously small. If you have 3 body decays, in our parity violation, 10 to the minus 3 couplings are enough to give you displacement. We've seen smaller Yukawa couplings than that. In the case of gauge mediation, I covered it up, but the sort of 10,000 TeV or 1,000 TeV mass scales can give you observable displacements, depending on the LSP mass. So you can there are some searches for displaced vertices. In my opinion, there probably aren't enough searches for displaced vertices. But on the other hand, they actually cover quite a bit of ground, even with a few of them, because these are they often require sort of involved new analyses, which is why they're not done all the time. But they offer often some pretty striking signals with low background. So there's an atlas search. Sorry, I'm reordering this relative to where it was in my notes. Right. So there's one search that looks for decays in the muon chamber. So you have, for example, have your collision point, got your tracker, calorimeters, and then muon chamber and atlas. Both of these happen to be atlas searches. If you have a particle that decays out here, see a lot of tracks in the muon chamber and nothing that came before. This is something that has pretty low background. The last search of this form, I think, that's public was just for a few inverse femtobarns. 1203, 1303. It's listed as a search for exotic Higgs decays because it was motivated early on by scenarios where Higgs decays into a hidden valley, but it's applicable to any of these displaced scenarios and has quite good sensitivity. Another possibility is, of course, just looking for vertices with the part of the detector that was designed to look for vertices. The issue here they actually had to make a dedicated trigger for this kind of activity in the muon chamber in the absence of anything else. You can be lucky twice and look for a muon to trigger on, just because you have to trigger on something, although this search could be done in every trigger, as far as I know, plus a high mass and high multiplicity, high track multiplicity decay in the tracker. Or rather, decay reconstructed in the tracker. So this could be just a millimeter displaced vertex, or it could be a decay inside the tracker. So when I say in, what I mean is less than or equal to the radius of the tracker within the volume contained by the tracker. And this, again, an Atlas search, hasn't been updated to the recent luminosity, sensitive to this. These displaced vertex signatures, so a more interesting case is if you have a displaced vertex that has no multi-track activity, just displaced photons, say from some of the other gauge mediation cases where the main decay is into photons. That can be that's the case where photons can actually be quite a bit harder to see. And I don't actually have the references, but there are also some non-pointing photon searches motivated by that scenario. These cases are smoking guns, but they're smoking guns that have to be looked for. So if you're lucky in this displaced vertex sense, then there's automatically very good sensitivity to those scenarios. What if you have prompt decays? Well, you could still be lucky and have some leptons from cascade decays, even some order 1 fraction of the time. Or you could have some photons from cascade decays. And it turns out that's enough where you can look at a relatively simple signal, something like, basically you look at the number of jets, you look at the scalar sum of PTs of the stuff in your event. In events with 1 photon or 1 lepton. And you can see from, say, gluino production, a rather noticeable, I mean, it's not, I don't want to oversell it. I wouldn't call it a pronounced separation. The waters of the Red Sea don't part between these two distributions. But the standard model definitely falls as you go up in both variables. And these signals have a lot of jets and a lot of PT and tend to be sort of clustered up where the standard model is falling. So that you could actually look in cross sections of these distributions. You would see shape deviations for the standard model, not just a normalization, but even something that looks vaguely like a hump, depending on how you slice it. So this has been done by CMS in the 1 photon case. Unfortunately, I forgot to write down the reference. It's a search for 1 photon and many jets with low missing energy or something like that, motivated by the stealth supersymmetry papers, which are sort of elaboration of this scenario here. You can also, I think, get very good sensitivity with a lepton in place of the photon. You really need one of these handles for this simple approach to have good sensitivity, just because the QCD background is about 3 orders of magnitude higher than the one lepton, about 2 orders of magnitude higher than the 1 photon background. So if you're lucky and have one of these handles, then this kind of simple cut and count analysis should be viable. I wrote a paper with Matt Strassler and Mary Angela about the 1 lepton case quite a while ago, but as far as I know, this search hasn't yet been done. But this is a general class of being lucky. Now, ideally, you don't want to have to be lucky. And so, there we go. So I want to talk briefly about this all-hadronic case. So let's say worst case scenario, right? Not very many cascade decays from your SUSY spectrum. And then on top of that, let's say the LSP just decays this way and doesn't produce top quarks, so no leptons there, just produces light flavor quarks in its decays. Then what you're left with is some process with a huge jet multiplicity and not much else. rather huge parton multiplicity. If I think about, say, gluino that decays to quark-squark, and that squark decays to quark neutralino, and then that neutralino decays to 3 jets, to three more quarks, then I have 2 of those happening all the time, then I have 10 quark production in basically every SUSY event. 10 quarks is not equal to 10 jets. This sort of parton to jet equivalence approximation works okay. You know, the probability of radiating off an extra jet or of 2 jets merging is less than 1 when you're talking about 4 jets. But it's a virtual certainty that some jets are going to merge and some jets are going to radiate when you're talking about a 10 parton final state. So you can't just say, I'm going to look for 10 jets. But there have been a variety of efforts to look for this kind of signal. So how would you look for this? Well, I'll just sort of list a few of the options. One option, which was pioneered by Scott and Reuven and then first done by the Tevatron CMS group at Rutgers, was looking for this resonant part of the signal by basically plotting invariant mass, some PT for 3 jet pairs in multi-jet events. And, you know, in a QCD event, these are both pretty correlated. The masses aren't on any particular resonance. But if you have some resonant process, then you're going to get a little tongue sticking out of the distribution. And so one can design some well-designed cuts to look for that tongue. This kind of thing has currently the leading has very good sensitivity to sort of intermediate mass, a few hundred GeV gluinos. At lower masses, even lower masses, the jets in that 3-jet event are almost guaranteed to merge. And so instead of looking at 3-jet mass, one can look instead at substructure of a single jet. You could also try to look at just overall number of hard jets. Say something like 6 jets above 160 GeV. That requires a lot of really hard splittings to pull off in QCD, and is kind of natural if you're talking about a high mass gluino decaying. So this is sensitive to M gluino after 5 inverse femtobarn atlas analysis, less than about, sorry, I can't resist writing this one out with 3 significant figures, less than about 666 GeV. So the atlas search that did both of those was an atlas 2012. Apologies for all my fiddling. (2012) analysis with 5 inverse femtobarns. There have also been several iterations of this strategy, Tevatron and CDF. I think this is unfortunately the area that I know the least about of the searches we've discussed, so I can't really do it justice. But I do think this is the area that actually has the most room for improvement. So there have been a lot of suggestions by theorists of different ways of using jet substructure types of techniques, grouping these jets into fat jets and analyzing them to more effectively analyze the jet multiplicity in these events. and search for that high parton multiplicity without requiring every parton to be a distinguishable jet. There's also boosted regimes in each of these cases. So I think there's a lot of room for new techniques to apply here, and also just the mapping out of how different models would actually look in these searches hasn't really been done to the same degree of thoroughness that it has been for, say, the JETS plus METS searches. I think it's very clear now what the different simplified models are that one should have in mind for this kind of scenario and what they look like. And it's significantly less clear over here what the sort of end of the story is. It's also clear that the gluino reach that you're getting, I mean, I mentioned this is the least lucky of all possibilities, so it shouldn't be surprising that your gluino limits are weaker. But this is still a pretty weakly constrained scenario, right? If SUSY is going to be really close to dead natural, this is, I think, the only place that's really left, is a spectrum without very many leptons with a light gluino decaying through our parity violation into light jets. And this could still be quite natural, and the bounds are crawling on. So we could probably give some thought to how to make these marches well. So that's where I'll end. Happy to take questions. I guess I'll just close by saying that on the whole, I mean, this is the same thing I said at the beginning. On the whole, with this is the one piece that hasn't really been resolved to my satisfaction yet, where I don't see the clear path forward. With this exception, I now feel like the LHC search program is actually pretty robustly covering most of the, most different final states about as well as it can, and will likely continue to do so. And that means that we're really at a sort of pivotal juncture where, from day to day, we're watching these limits inch along, or from conference to conference, we watch them inch along. But looked at over a 5-year period, this will be a time when we learn decisive things about the viability of a sort of very natural models of supersymmetry, as well as the viability of other natural models of new physics. We should get everything we can out of this machine. It will be a long time before we get new data to answer these questions. Maybe a very, very long time. We'll see. So it's really worth thinking about all the corners that can be explored with the LHC. And we're going to learn a lot from it. So that's it. Yeah.
So there's something like 4 or 5 R parity violating parameters, including one bilinear R parity violating parameter. To what extent and you can suppress something like photon decay in different ways by choosing these parameters. So to what extent do you feel that all these possibilities have been explored?
Right. So, okay. So I forgot to say this in the context of the R parity violation. I focused on the hadronic one because the leptonic ones, I mean, multi-lepton searches at this point have very low missing energy requirements. And so the minute you have a decay process that provides you with high efficiency with leptons, the odds of finding it through those multi-lepton searches are quite good. And I don't think it warrants as much sort of dedicated, concerted effort to look for the R parity violation beyond what's already been being done to look inclusively for multi-leptons. Some thought should certainly be given, but this is much more of an experimental question, and thought is being given to it, to dealing with the sort of tau-rich versions of those situations. But A, that's experimental. B, taus decay leptonically sometimes too. And C, that's already known. In the photon case, so in the case of the gauge mediation, I sort of highlighted the non-photon cases just because the photon search is now so canonical that one barely needs to mention it. It's not exactly an often overlooked window. Now, a second question you can ask, that I don't think is the question you asked, but maybe it was, is by going into these parameter corners that I'm talking about that are hard to see, am I really doing a lot of other tuning and just not calling it that? I mean, that's a question I think one should ask when having this kind of discussion. But I also think it's a question that's hard. I mean, these are dimensionless parameters that we're talking about, first of all, or sort of in the case of the gravitino. Well, yeah, it's a ratio of dimensionful parameters, but an order 1 ratio that's sort of controlling the dynamics. We don't know what the high energy physics is. We don't know where SUSY breaking comes from. There are models that realize all of these textures. There are probably models that realize other textures that we haven't thought about yet, one of which could be true. And it's all sort of discrete choices, right? You can achieve by a discrete symmetry choice or geography choice in an extra dimension which of these couplings are significant and which ones are small. So yes, there's some sort of 1 in 5 tuning of which, if you want to call it that, of picking which nature we actually live in, but it's not like you have to tune by 10 to the 5 to get one branching fraction suppressed by 10 to the 5 relative to the other. Maybe I should say, in the case of the GMSB type decays, if you wanted to get, say, all Higgs or all Z rather than a mixture of the two, you do have to tune to get that. But the suppression of photons can happen just by decoupling the BNO. Right. So at least in this sort of, so assuming that, so I know for light gluinos, the sensitivity of LHC is about, or high luminosity LHC is in the 3 TeV gluino mass neighborhood. And the sensitivity of the high energy LHC doubles to like 6 TeV. So those are the estimates I've seen from some of the CMS projections for European strategy that I was looking at last night. So that corresponds to tuning in the neighborhood of, 2% to 0.5% from the gluino. I don't know how the stopped bounds and how the bounds on all these different scenarios will evolve. I think my suspicion is that those will scale somewhat similarly, with the possible caveat that looking for the stops as they get heavier is going to require very different technology than the ones that's been used so far because of boosting and lower B-tagging efficiencies. But in a sense, if you can look for the gluino, you're already setting those bounds, whether you can look for the stop or not. So to me, the real issue, though, is what's going to happen with these kinds of demon scenarios, where I mean, the limit won't stay at 666 GeV forever, I don't think, but but it's likely to be the sort of the hole that survives and into the sort of tens of percent tuning region for a long time. Yeah. Why the Higgsino? Yeah, it's because the Higgsino mass contributes directly, just at tree level, into the Higgs mass matrix, right? So in some approximation, just mz squared over 2 is set by mu squared plus mhf squared plus corrections from beyond the MSSM. So, I mean, we can have other stuff here. There's, I would say there probably should be other stuff here unless the stops are quite heavy. But just directly, in order to cancel, to get to Higgs mass, to the physical Higgs mass scale that sets the VEV, sets the Z mass, sets the Higgs mass, you need to be canceling other stuff against mu. Right? So if mu is very large, then there's just intrinsic tuning of these different tree level contributions against each other. The same can be said, by the way, of the heavy Higgs searches, right? If you're doing searches for the heavier SUSY Higgses and set bounds, the problem is that those searches are very sensitive to tan beta because they really rely on large couplings to be quarks. But if you set stringent bounds on the Higgs couplings, on the heavy Higgs masses of the MSSM, that would also be contributing at tree level. You can say that's another fine tuning. Yes.
So I would put a lot of weight on what you just said. That is, in terms of gambling on the kinds of states that you should expect in this kind of scenario, would put a ton of weight on that tuning that you just point out. It's almost a tree-level tuning consideration that you have to take into account. But as Nemo pointed out the other day, you can view the search for supersymmetry sort of from top down, writing very high energy scale models and running them down and looking at, and this consideration just looks like you're stuck with it and there's no any way around it. But if you sort of look at SUSY just as a model from the bottom up, don't be very ambitious, don't try to get to the scale, none of that. Just try to understand the hierarchies close to Earth, just from here to 10 TeV or 100 TeV. There is this sort of funny out that it looks like you can just give in some phenomenological Lagrange, you can sort of give a Higgsino mass, which is a SUSY breaking mass, which doesn't enter into the bosonic Lagrangian in this way. And it doesn't look from this bottom-up perspective very tuned. And it's just an example of where, of course you should put most of your money on what you just said. And yet, my sense is that we really need to get closure on at least maximal naturalness.
Yeah.
And somehow there's enough of us that we should be pushing in all those directions, even that kind of a loophole. And it changes things. It's not a minor detail in most of these searches. The low-lying end of the spectrum, for somebody at the Planck, for a string theorist, the low-lying end of the spectrum is pretty, it's a matter of details. And for us, it's everything. And that seems to matter.
Right. Well, I'll partially agree, and to some extent it does change everything. But on the other hand, so another class of searches, yeah, so germane to that point, another class of searches that I should have mentioned is, of course, the searches for charged LSPs, R hadrons, that live long enough to exit the detector, or at least pass through a significant fraction of it. If the Higgsino mass is raised, then that's certainly a fairly natural possibility, but that's also very tightly constrained by these R hadron searches. Those are, if anything, even better. Then you say, well, is there a light Higgsino, or is there some other neutral LSP that's accounting for the absence of R hadrons in all of these models? And then, whether it's a Higgsino or a Bino or a Wino, certainly matters to direct stop searches, for example. It matters a lot less to the searches for the gluino. It still matters. You need a slightly different texture of searches to see the constraints, but they are not different by, there's roughly the same sensitivity from that collection of searches regardless. So as a formal point, it is a good one, and thanks for mentioning that, that you could have a correction to the Higgs-Zeno mass beyond mu, just from SUSY breaking. As a sort of empirical point, I don't think it's, at least I don't know of examples where it would really qualitatively change the story. So you can look at, so it does lead to somewhat, it can lead to simpler RPV processes, where these kinds of resonance search approaches are much more important than the multi-jet ones. That's certainly true. But again, both of those are being done. And both of them have pretty terrible sensitivity when compared to the other scenarios, but yeah. But actually, I didn't emphasize that enough, right? If I remove the neutralino from that story and I have, say, directly a gluino LSP or a stop LSP, then we're out of this multi-jet regime. And you really have to go back to looking at smaller number of jets in a resonance, different class of searches that, I mean, both are being done right now in a somewhat primitive way. It's worth making both of them less primitive, so it's worth emphasizing both of them and continuing to think about both angles and improve them. And the other thing I should say in that context is even if you don't have, say, the Higgsino Higgsino masses from another source, it's silly to not consider a model that has been a stop LSP over a Higgsino LSP because it's 3 times more tuned, or 10 times more tuned than the analogous model with a lighter LSP. We don't know what nature's spectrum is, right? That's the danger of the word choice natural SUSY manifested yet again. Yeah, I actually don't know that number either. I know very little about the direct electroweak searches, and was counting on Patrick to cover that part for me. But does anybody know?
I'm not sure that they'll ever figure it out. Direct example. Yours is the now question.
if you have significant splittings, there's some, right? But if it's pure Higgsino, then yeah.